Lesson 7-6, Superposition and Interference. It can happen, and often does happen, that two or more wave pulses move through the same space at the same time. When two or more waves are present simultaneously at the same place, the resultant disturbance is simply the sum of the disturbances from the individual waves. So in other words, waves add. And what's particularly adding is the amplitude. So the amplitude will add between all the waves that are at the same place at the same time. All right, here we have two waves. We have the first wave and the second wave pulse. They're going towards each other. When they hit, so they're both at the same place, just adding the two amplitudes together. And that gives you the resultant height at that point. After they add together and pass through each other, then they go back to the same wave pulse, same height wave pulse that they were before. So they only add together at the same place at the same time, but after they go through each other, it's back to the way they were. It's another case. Here's an upward pulse meeting a downward pulse. Their amplitudes would add, so we have the up plus the down adds to make 0. So at that point where they meet, there's 0 wave. And then they pass through each other, and you have the up and the down. All right, these two wave pulses are moving towards each other at 1 centimeter per second, or 1 square per second. After 2 seconds, what is the height of the resultant pulse? If they're moving at 1 centimeter per second, after 2 seconds, they'll have traveled 2 centimeters. So redraw the pulse after they've moved over 2 spaces. So the bottom one is going to look like that. The upper one is going to look like that. Now, what we're going to do to get the resultant is add the heights. So 0 plus 0, 0 plus 0, 0 plus 0. Our next spot we have 2 and negative 4. 2 and negative 4 is negative 2. Next spot we have 2 and negative 4. It's negative 2. So we're adding the heights, the amplitudes. Then we have 2 and 0. 2 and 0 is 2. And then here we have 2 and 0. And then 0 and 0. And then there's no more pulse. So the result is the thick red line, which I got after moving each individual pulse 2 places, because it was 2 seconds of motion, and then added the y values of each of the points of each of the graph, the heights of the graphs. So the resultant at x equals 2 appears to be 0. At x equals 4, we're at negative 2. And at 6, we're at positive 2. All right, that last example is, contrived mathematically to get the idea. In real life, what happens? Well, if we have two speakers facing each other, both speakers produce the same sound at the same time. I'm going to say they're 1 meter apart. Or the wavelength's 1 meter. So you can see the speaker here. We have some crests that go out. The other one has crests that go out, and they meet right here. So we'll have a crest meeting a crest. So that'll be the amplitudes add. And then they move on, and then we'll have the rarefaction will meet, or the troughs if you like. So those would add. So it's like we have the crest meeting and then the troughs meeting. So we get this bigger wave where they're added together. So it's going to be twice the amplitude. It'll be louder. What if one of the speakers is moved back half a wavelength? So now the wave from one speaker has to go an extra half wavelength. So it now has a rarefaction, meaning a condensation, or a trough, meaning a crest. The trough meeting the crest. That adds to make nothing. And then this condensation will meet this rarefaction, which adds to make nothing. So at that point, it's going to cancel out. And you won't hear anything. There'll be no perceivable sound at that point. Now, you have two ears, and your ears are kind of biggish, and they pick things up. So if you're at this point, remember your head actually has an ear over here and an ear over here, so it won't sound like exactly nothing. You'd have to have a microphone to pick it up at a very specific point to notice. But you probably would notice that it's quieter there. All right, this is called destructive interference because the wave has been destructed and isn't there. So remember, as it goes past that point, the wave is back to its original sound. It's just at the point where they meet and the amplitudes get added that it's going to be less. An application of how this is useful are noise-canceling headphones. So you're wearing these headphones, usually in a noisy environment, and this noise is coming in. Inside the headphone, there's a microphone and connected to a speaker. It produces a completely inverted wave. If you think transverse waves, flips it completely upside down. Whatever was a crest is now a trough. Whatever was condensation is now a rarefaction. So these all line up. And since they're exactly opposite, they add up to make nothing. And you don't hear anything. There may be a ton of noise, but it all gets canceled out and you don't hear anything. All right, we do know waves spread out. So in real life, it's more like this. So we have these two speakers producing the same sound. Wherever two condensations or crests, where the dark circles are, meet, you get constructive interference, and it's louder. Where two rarefactions meet, the same thing. But if you get one condensation and one rarefaction meeting, they're going to have destructive interference. It'll cancel out. So as you move through your room here, you're going to have some places where it's louder and some places where it's quieter. The constructive interference would have twice the amplitude, so more energy, loudness. Destructive interference, the energy would cancel out. Another interesting applications of superposition and interference are beats. We were looking at when two frequencies were the same. You get just the straight constructive and destructive interference, giving twice the amplitude or else no amplitude. But what if the two frequencies are just slightly different? What then? All right, so here are two tuning forks. One's producing 440 hertz, the other one 438 hertz because we put putty on one of them. And so if we look at where they line up, we have a condensation meeting with a rarefaction. Cancels out. Destructive interference. Here I have a condensation and a condensation. It's going to be constructive, be louder. And then, condensation and rarefaction is going to cancel, destructive. Here, condensation and condensation be louder, constructive interference. So this is going to go from quiet to loud to quiet to loud and back and forth. Here it is. This is a different graph. Here, crest meets trough, you get nothing. Here we have a trough and a trough, so what's the biggest trough? Crest and trough is nothing. Trough and trough gets a bigger trough. Crest and trough is nothing. Part way in between, we're meeting part way. So you can see this general shape here of it's going to get quiet, loud, quiet, loud. So you feel this pulsing back and forth. And those are called beats. This pulsing you get is called beat. The beat frequency is simply the difference of the two source frequencies. So the beats, the frequency of the beats, is just the absolute value of the two different frequencies. Beats give you a simple way to tune musical instruments. If your notes are out of tune, you play the notes together. If they're out of tune, you'll hear beats. So you adjust the tuning and you try again. The frequency of the beats becomes higher, goes wah, 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 adjust the other way until you'll hear very slow beats, wah, 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 until you keep adjusting until you get no more beats. And when there's no more beats, you're in tune. Two car horns have an average frequency of 420 Hz and a beat frequency of 40 Hz. What are the frequencies of both horns? Well, if we have an average, that means we add them together and divide by the number of numbers. And the beat frequency is 40. So that means when we subtract them, I should get 40. Well, this looks like a system of equations. I'm going to take the first one, multiply it by 2. And then I can do simple linear combination or elimination. I'll get 2 F1s, F2s cancel out, and 880. Divide by 2, and one frequency is then 440. What would the other one be? Well, F1 minus F2 is 40. So if F1 is 440, do you agree that F2 must be 400?